Hi everyone, I'm Sharon Carmel, I'm the founder and CEO of Beamr, and we're going to talk about how we are making a breakthrough with Intel hardware encoder binded with Beamr, making video much smaller and actually higher quality than software coders. So what we stand for in video, there's like a balance between the quality and how much video and how fast you can encode the video and how much bitrate you consume. And I think that we made a name for ourselves for software video encoding, that we can have either the best quality or the highest density on x86 platforms. And our content adaptive technology is where most of our IP is how we can reduce the bitrate of video while committing to the quality. And everything that we do, we started with photos and now we are supporting AVC and HEVC standards. Everything that we do is within the standard. So you're encoding using Intel hardware, for example, using our technology as well. But on the decoding side, it is the plain vanilla decoders that comes with every phone, TV, or computer. We are known for having a lot of intellectual property. Actually, this Sunday we got our 46 granted patents, all in the area of video coding and video optimization. 11 out of the 46 patents are in the video efficiency and video quality area, and 35 are actually in video optimization. This is our lion part of the IP. So what's content adaptive video encoding? Videos can be treated alike, and this is usually what's been done. Everybody knows that if you're taking a 1080p video, and if it is HD video, if you're going to have a AVC encoder, which is a pretty good a quality encoder, with 6 megabits, you're gonna do fine with all of the videos. So no matter what the content is, if it is action movies or a TV series or animation movies, okay, you'll do fine. But everybody who also is an expert in the field of video coding knows that you don't need 6 megabits for the entire movie. And different types of content also needs different allocations of bitrate. And what we've been able to do is to develop a mechanism that can automatically determine per frame of video whether you need the maximum allocation for the video set by, of course, the user, or can we use less. So even with the high action movies that are very demanding, okay, we can have reduced video bitrate of like 20%. And when it comes to simpler content, we can actually cut it by half. And this is very dependent. Also in the animation movie, there may be scenes that you need the entire 6 megabit allocation. But for the most frames, you probably don't need that, and the averages are going dramatically down. And our ability is basically to create a program that can, in a very reliable way, create a video that will not look less good than the 6 megabits on each and every frame of it, but where we can, we will actually reduce the video while committing to the quality. The benefits are pretty obvious. We'll just touch on some of them. When it comes to cost, then of course, the delivery cost is substantially going down. And when we're talking about storage, to store all of this video, again, pretty much the same ratio. For user experience with video streaming, there's something we call adaptive bitrate. We are actually creating lots of bitrates for the video, and depending on the networking conditions, you're switching between the different video layers. And what we're offering is that, let's say you're having only 4 megabits, you will be able to get the full HD video with Beamr, because we are optimizing the video, let's say, for 4 megabits, and you don't stay at the 6 megabits if you would use just regular encoding. So we are improving the quality. Video starts faster because sometimes there's need for a buffer, so the video can kick off faster. And of course, when there's network fluctuations, there sometimes can be buffering events. Of course, with reduced bitrate, you get less buffering events. So how does this magic work, and how we can guarantee the quality? Basically, our method is not to emulate human vision. We cannot actually model a human vision today. I think nobody can. But what we can do is we can measure how video encoding is actually distorting or reducing the video quality. It is actually damaging the video in a very particular way that can be actually quantified. And this is what we're doing. So for example, for an image of a video, there are edges of that image. There's the contour and there are kind of lines that are very apparent. You can just create a filter and see these edges. And then if we are creating a candidate frame that is actually lower in bitrate, we can see if these edges are actually being preserved or not. Same for texture. There are mild texture changes that our eye will not be sensitive for, but there are some that we will be sensitive for. There's area of interest. Sometimes, we are, of course, more sensitive to faces, to skin tones. If we can detect this area of interest and we can apply more emphasis on quality in these areas, that means that we will probably create a perceptually identical video and we can actually reduce the bitrate as long as we are making sure that we are not damaging critical areas. And there's another part which is the tiling and pooling. What we need to know is that not all of the errors that we are creating while we are compressing video are the same. Let's say if I will now have a big X on my forehead, it will be very apparent. But if it will be like somewhere, on the side, it will be less apparent. So we need also to pull the error and to know, if it is in a significant area of the image or not. And this is a part of the things that we are doing. But how we can actually guarantee that the quality will not be hurt. And for that, we have a closed loop mechanism. So we're using an encoder. In the presentation that I will show you later on, we will use the Intel hardware encoder. And what we can do is that we can create multiple candidate frames. Some of them are in the, let's say, 6 megabits that was initially ordered by the user, but we can create candidates for 4 megabits and 3 megabits. And then we can actually determine if they're actually perceptually identical or not. If they're not, we'll go with the source, because we cannot reduce this video payload because you just need all of the bits. But in some cases, and in most cases actually, we'll be able to use a lower bitrate frame candidate, but everything is controlled, and only if it is perceptually identical, we will let this frame out. If not, we will use the source frame. So we can reduce the bitrate and we can guarantee the quality, and that's a part of the sophistication of our system. So we took this system and we decided to integrate it with the Intel Media SDK. And the Intel Media SDK has been out there for a long while. It's a very sophisticated software stack, not just for video encoding, but it does a lot of other image processing capabilities. We're focusing on video encoding and the standards like MPEG, AVC, HEVC, and VP9, and of course future codecs that will be out there. Our content adaptive technology is pretty much codec agnostics, as long as they are using block-based coding techniques. And together with Intel, we have adapted the API of Intel Media SDK and incorporate our content adaptive mechanism to be a part of the encoding process. At the very bottom of the image, we have the hardware. We have the video acceleration API that we can actually access through the Media SDK. The Media SDK is an open source project, so for us as developers, this is the way that we are innovating. And in the specific project, we actually got a lot of help from Intel adapting the Media SDK APIs and some of the driver APIs. And of course, there's you, the actual users, where do you use FFmpeg, or let's say you have a video editing software like Adobe Premiere or Cyberlink or any other. You can actually use the Media SDK and enjoy content adaptive encoding. So this is the way that Media SDK is built, and now I'll show you what actually we did. So inside Media SDK for video coding, there's an external bitrate controller. This is actually an ability not to use just the built-in hardware encoder rate control that can actually control the bitrate of the video, but actually to have external control that runs on the CPU that will enable us to control the video. And with the right APIs, we just took our content adaptive bitrate library and we integrated it and made it a part of Intel Media SDK. And now as a system, you have a closed loop system that can use the Intel hardware, which is super fast. Today with the Gen11 graphics and Ice Lake, you can run 4K P30 or even P60 video encoding in HEVC. And that will be just in, I don't know, 10 or 15 watts of cost. Okay, while if you're doing it software only, which is what is our legacy encoders are doing, okay, you need probably 5 or 10 times the power just to create the same video. And with Gen11 graphics, you have pretty high quality, and that's very, very powerful. So now, by just controlling the hardware encoder, we've been able to create amazing quality video at very low bit rates, thanks to, of course, a very good hardware encoder and our ability to control it using content adaptive bitrate. So, how does that work? A regular video encoder will just have an input frame, it will have the rate control, and it will output it, and will just go through the frames and crunch through the data. With CABR, we're getting the initial frame, and we're measuring the quality. We can have some pre-analysis, and we can say, how complicated this is. Then the Intel encoder actually enable us to create 3 additional candidate frames at the same time with lower quality. And we're doing that at the same time. We can run our control model, and we can determine if they are perceptually identical or not. So not that we're getting just the first regular encode, but at the same time we're getting 3 additional encodes that we can choose from. And this creating like a plurality of options for us to hit on the target and to do it in real time. After we're doing this analysis, we can select whether it's the source frame because there's nothing to reduce, or in most cases, one of these 3 candidates will be good enough and perceptually identical and will actually output it. And this is how the system works. Now, why do we say that this is a game changer? Why do we say this is a tiebreaker for video coding? Eventually, video encoders are standard. And with enough work and maturity of generation after generation of video coding, the video encoders are good, to sometimes very good. But there are applications that requires a lot of bandwidth. And one of the emerging cases that I wanna touch on is cloud gaming. With cloud gaming, we have a system that everything runs in the data center. So your console is actually virtualized, it's running somewhere in the cloud. It of course needs lots of GPU for shading and rendering and texture mapping. And eventually, you are transferring a video and audio image to the end user in real time, in very low latency. And the user will just use his controls to give some input back to the system. Everything happens in the cloud. And for that, you need to create very fast, low latency video encoding, which is a huge challenge. And this is what the market is now shifting from consumption purposes. So what we've seen lately is that we have Google Stadia announcing, that they're going to go with that cloud gaming platform called Google Stadia. And what you see is that they are talking about 20 to 30 megabits per second to run video games on the cloud. That's huge. That's actually almost, unless you're living in a very populated area with awesome infrastructure, you don't get that kind of bandwidth. And the reason that we need so much bandwidth for video is that you have actually some tools that in the video coders that you cannot use, like B-frames, that's like 20% that you just lost right there. You cannot look into the future to make better decisions because this is real time. If I'll wait another frame, I'm losing 16 milliseconds, that's very bad. Here goes another 20 or 25%. We're not running at 25 or 30 frames per second like VOD, we're running at 60 because this is what gaming is requiring in order to give you the user experience. And on top of that, 3D is terrible to encode. Just harder to encode for every video encoder. So here you go. This is the 6 megabits for 1080p, but now 60 frames real time. Instead of 6 megabits, bang, we're at 20 megabits. And that's a very large handicap. So we took a few cloud gaming and we encode them at 21 megabits per second using Gen11 graphics, and at the same time we used our integrated content adaptive bitrate library for the same thing, and we got 25 to 40% reduction in video bitrate. Now I hope that you are intrigued enough to see that. So this is a part of Grand Theft Auto 5. It was rendered in 60 frames per second. What you can see is actually one of our developments called the Beamr View. It's a stereoscopic player. So these are two synchronized decoders that are running at the same time. And you can see also the video properties. So on the left-hand side, this is Intel Gen11 graphics, 21 megabits per second, 60 frames per second, and that's the quality that it can produce in real time, which is pretty good. And on the left-hand side, this is the same Intel hardware encoder. The same thing, the same hardware, but now controlled with CABR that can monitor that in a closed loop. This is only 12.7 megabits per second, 40% less bits, which is pretty amazing. So I hope you like what you see. Where we're at. Currently, we had a successful POC with Intel Gen11 graphics, and we integrated content adaptive bitrate with Intel Media SDK. And what we want to create is a commercial product running at 30 frames per second for VOD and live video broadcasting, but also a 60 frames per second product that will be available for cloud gaming. And that's the holy grail here. And we believe that this is achievable even with the Gen11 graphics that is currently shipping. Obviously, there are going to be newer generations that are faster and better, but this is already awesome for us. And that's it. I'm open for questions.
What do you use? A variable bitrate or constant bitrate?
Has to be variable.
But you write constant bitrate on all videos and tables of statistics. It is some average value?
Yeah, it's the variable bitrate usually works in an average window of 1 second, a moving average window. And you give it a slack called VBV, the variability that you allow it to go up and down. So, yeah.
Okay. And you use only integrated GPU? Because if you run on cloud, I think there are no consumer CPUs of Intel. There are Xeons with some discrete cards.
I will let the Intel guys talk about their plans. So
what you are using?
Currently, this is Gen11 graphics available on laptops and desktops. So it's the consumer product.
Okay, thank you.
But these cores are a part of the GPU family that is coming. So I think that again, having a good encoder is one thing, and having the right APIs and the openness of the environment is another thing. And I think that Intel is definitely ahead of the curve in terms of allowing third-party developers to take additional technologies that can actually take the video efficiency, the coding efficiency of a hardware encoder, which is already great, and make it twice as useful. Just to give you an idea, the difference between the AVC standard and HEVC standard is like 40% efficiency. Just think of this additional 40% efficiency that we just brought into the existing implementation of Intel's HEVC encoder, and the same technology is accumulative to AV1 or VP9 or AVC. So this is a sustainable advantage that once you have the right APIs, you can definitely have a game changer or a tiebreaker when you are comparing your performance to the others, because bitrate matters a lot, especially in real time.